So longitudinal mechanical waves. Okay, Shikhar. Okay, the physical example of that being sound. So the definition of longitudinal waves we have seen before, that if medium particles oscillate along an axis, okay, parallel to the direction of propagation, in a mechanical wave, then it is called a longitudinal mechanical wave. Okay. So the one-dimensional longitudinal wave is a sound wave propagating along a long windpipe, or such a pipe is also called an organ pipe. And by long, we mean it should be literally extremely long, so that the other end of the pipe is at x tending to infinity. So if this end is at x equal to 0, now, for example, if we have a piston at this end, which is attached to an oscillator, in fact, the piston itself is an oscillator, let's say. Okay, so it oscillates with a frequency of f and an amplitude of a. So this is an oscillator displacing air, okay, longitudinally. At x equal to 0 with a frequency f and an amplitude a. So what happens is that as this oscillator goes back and forth like this, it displaces the air also back and forth like this. So at any general point x equal to x, at any point p like this, what happens is that the displacement, or what we call the longitudinal displacement, which is along the x-axis, mean position at x equal to x, okay, that becomes some amplitude into sine omega t minus kx plus some phase constant in general if it's traveling along the positive x direction, where S naught is equal to the longitudinal amplitude. Okay, in this case, S naught will be equal to A, the amplitude of the source. Omega will be equal to 2 pi f, where f is the frequency of the source.
So same equation, right? For sound waves
Yes,
also.
exactly. The only difference is that now it is not a displacement along the y-axis, it is a displacement along the
X-axis.
x-axis. Okay.
तो सर जो s होगा वो a के रिस्पेक्ट में लिखेंगे.
हाँ, s is a function of x and t both, है ना? So at a general point x equal to x, the displacement along the x-axis from the mean position at a time t is given by this equation, if it is traveling along the positive x direction, right? And k is equal to omega by v, okay, where v is the propagation speed. So again, depends on the physical properties of the medium.
Sir,
Yes.
sir, so longitudinally amplitude would be the difference between two compressions, right?
Yes, we are coming to that also, that this kind of thing creates compressions and rarefactions. Okay. But right now you can just think of it like, yeah, it is the distance between 2 points, minimum distance between 2 points which are oscillating in phase.
Yes.
And yes, they would reach their compression simultaneously, they would reach their rarefaction simultaneously, they would be at mean pressure also simultaneously. Okay. So K is also equal to 2 pi by lambda. So V is equal to F lambda. So again, you have that thing that in the equation V is equal to F lambda, F is the property of the source, V is the is determined from the physical properties of the medium, independent of the source. So that thing is still the same. So a particle with mean position x equal to x, okay, oscillates between the position x equal to x minus s naught to x plus s naught with frequency f. harmonic. Okay, so next we'll understand that how exactly the wave propagation speed depends on the medium properties. Such that for sound propagating through a fluid medium, that is inclusive of liquids and gas, the speed of sound is given by square root of Bulk's modulus of elasticity divided by density. So for an ideal fluid, Bulk's modulus is a fixed quantity at a given temperature, and density is also fixed because it is incompressible. But through a gaseous medium, as sound is propagating, as we have discussed in thermodynamics before, or actually later, okay, we have discussed in terms of properties of matter that Bulk's modulus is a variable quantity, instantaneous quantity for a gas, and its value also depends, its formula also depends on the type of process happening. So we'll discuss that in some time. Just make a note of this fact first.
Sir,
Yes.
can you explain the second point for the velocity when you such that the source start for sound propagation through fluid medium? I'm not understanding. Why is it that?
Such that for sound propagating through a fluid medium, which is either liquid or gas, the speed of flow is equal to square root of Bulk's modulus divided by density. Is it clear now? Uh, just a minute, I will share the file again. Just a minute, people. That program is rebooting. Yeah, so back online with it now. Yeah, so this is just a direct formula that I've written, which comes from experimental evidence. Okay, it's a factual thing that the speed of sound depends on the medium properties in such a way that when we are talking about speed of sound through a fluid medium, it depends on these two properties: the bulk's modulus of elasticity and the density, the volume density, that is mass per unit volume, that thing. Okay, now whereas for sound propagating through solid medium or longitudinal waves propagating through solid mediums, the speed of sound is given by a similar formula. Just a moment, guys. I'll have to restart this whiteboard program once more. Just hang in there. Yeah, so in case of so Bulk's modulus is just replaced with Young's modulus of elasticity. So for example, a metal can have Young's modulus of something like this, let's say. And a density of something like this, let's say. So speed of sound, you can see. I'm just showing you what kind of order of magnitude the speed of sound has. Through a solid metal. Okay. At room temperature, speed of sound through air is approximately 340 meters per second. So sound propagates much, much faster through metallic media, or for that matter, any solid medium. Even any liquid medium, because Bulk's modulus is large comparatively for liquids, and Young's modulus is pretty large, especially for metallic type of solid materials. Oh yes, my mistake. This should be 1 by 2 into 10 raised by 4, so 5,000 meters per second. Now we look at a specific section. Just a minute. Yeah. Speed of sound through a gaseous medium. So audible sound causes adiabatic compressions and rarefactions in a gaseous medium. Adiabatic because they are very fast. Because the frequency audible sound is in the region of 20 hertz to 20,000 hertz. Okay. So fast can be approximated as adiabatic, as we have discussed earlier in thermodynamics, because fast means there isn't enough time for heat exchange. So Bulk's modulus for adiabatic process is equal to gamma p. Okay. PV to the power gamma is constant. So if you differentiate this, you have this relation of it. So speed of sound density, and then further using the relation which comes from the ideal gas equation. We have so this is speed of sound through an ideal gas of molar mass m in kgs at absolute temperature capital T. Yeah, Rakshit, this is, I'm just giving a quick recap of Bulk's modulus calculation for thermodynamic process. So for a gas, Bulk's modulus which is defined as volume stress upon volume strain, is defined as modulus of instantaneous change in pressure dP, which becomes a volume stress upon dV by V, which becomes a volume strain. Okay. So this is a concept that we had discussed in properties of matter, and then we had gone on to discuss how to calculate the bulk's modulus in various different situations like adiabatic process or polytropic process or isothermal process or whatever. So you can just do a revision of this section from properties of matter later if you like. Okay. Just make a note of it over here. Okay, so by the way, just from a theory knowledge point of view, this particular formula that we have for speed of sound, this is called the Laplace correction formula. Because previous to this, sound was assume, create isothermal expansions and compressions, and speed of sound was given as square root of RT by M, because for isothermal process pulse modulus is P, but this is an inaccurate formula. Both theory wise wrong also, and also experimentally when the values were compared with respect to the theoretical value from this formula, it was found to be incorrect. So anyhow, let's look at a quick example. Want to find the speed of sound through nitrogen gas at 27 degrees C. So N2 will have gamma equal to 7 by 5 and molar mass as 28 grams. So there is 28 into 10 raised power minus 3 kg. So we'll substitute in SI unit. This will give us the speed of sound in meters per second. And if we calculate that, comes out to be something like this. Comes about close to 350 meters per second. So atmospheric air has 78% nitrogen. So you can see that it's that kind of order of magnitude, like the speed of sound through air at normal temperature.
Can you scroll up?
Okay, so this is all about speed of sound. Okay, I will scroll up, Devansh. Just give me a moment. Okay, now let's move to the next part now. Let's understand how or longitudinal waves passing through a medium
समर माइक बंद कर
cause compressions and rarefactions. That is pressure variations. Now this is pretty easy to understand, but now we have to represent this with an equation. So let's understand it like this, that imagine, so our one-dimensional model of longitudinal waves, that through a windpipe we are having these longitudinal oscillations happening. So we take this as a x-axis extending to infinity on this side. So as we are creating disturbances like this, so if you imagine a section of this pipe which is between x equal to x and delta x, so x plus delta x. So this is a section of the windpipe bounded by two surfaces of air with mean position at x equal to x and x equal to x plus delta x. So it has an unstressed volume where A is cross-sectional area. Okay. Now what is happening is that the boundary, that is the air surface at x equal to x, okay, oscillates by the equation, let's say this, F. Okay, stop hauling. Okay, just a minute. What happened? No. 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 Okay, whereas the other boundary oscillates with a slight phase difference, because its location is different. So if we consider the other boundary, just a second. That has a displacement S plus delta S in comparison, because it's at a different location. So its displacement at any point of time is different. So this means that its stressed volume that is equal to therefore its volume strain is the change in volume divided by the natural volume or the unstressed volume. So that is delta S by delta X.
Yes.
So if you imagine this cross section of air, okay, so what is happening is that imagine these are the two boundaries in the natural situation, okay, when there is no sound wave propagating. But with the sound wave propagating, they are oscillating, but they are not oscillating in phase. They are oscillating with same frequency, which is the frequency of the source. But because they are at different locations, they are having a phase difference. So alternately, they are coming closer, they are moving further apart, coming closer. Okay. So like this, if you imagine any cross section of, I mean, any volume element of air within the pipe, you'll see alternately it is compressing and expanding. Okay. So when this boundary has a displacement S and the other boundary has a displacement S plus delta S, the distance between them has become how much? It has become delta X plus delta S. So that's why the stressed volume, that is the volume when they are under stress because of the pressure, because of the sound wave propagating, has become this. It has become the natural volume A into delta X plus the excess volume A into delta S. But that delta S can alternately be positive and negative. So alternately it is compressing or expanding. So if we take delta X to be small, or delta X tending to dx, then delta S by delta X will become del S by del X. So it will become del by del X of S as a function of X and time, which is S naught sine omega t minus kx plus phi in this case. Okay. So the volume strain at any given point, the instantaneous volume strain is becoming this much. This is the volume strain. Now by Hooke's law, volume stress to volume strain ratio is equal to Bulk's modulus. So the volume stress is equal to Bulk's modulus into minus of delta V by V. Because we actually write this like this, that, with a mod. Okay, so cos. Okay, so we'll do more analysis on this. Okay, just write down up to here first. One more thing you can note down here is you can see that because cos omega t minus kx plus phi is an alternating quantity between negative and positive values. So therefore, the volume strain alternates between negative, which means that there's a compression because the volume is decreasing, and positive, which means there's a rarefaction. With frequency, so the propagation of a longitudinal sound wave through a fluid medium like this causes pressure variations, causes alternate compressions and rarefactions. Okay. Okay, so now what we do is this volume stress delta P, it is written as a function of x and t given by P is equal to a pressure amplitude into sine omega t minus kx plus 5 plus pi by 2, where P, what we write is actually the volume stress. It is not the net pressure. P naught is what we call the pressure amplitude. And omega is 2 pi f, where f is the frequency of the source. So basically longitudinal displacement wave S equal to S naught sine omega t minus kx plus 5. This creates a volume stress. We call this a pressure wave. So the phenomena of longitudinal waves passing through a medium causes a pressure wave. The pressure wave have pi by 2 phase difference with respect to the displacement wave. And the pressure amplitude is directly proportional to the displacement amplitude by this formula. So the larger the amplitude of displacement, obviously the larger will be the pressure variation. But also the pressure variation has a pi by 2 phase difference with respect to the displacement. So the meaning of that as usual is that when the medium particles are at the mean position of their oscillation, that is when the stress is maximum. So either it will have a compression maximum or a rarefaction maximum at that point of time. Whereas whenever the displacement of the medium particles has reached the extreme position of its oscillation cycle, at that instant, at that particular position, the pressure variation will be zero. The volume stress will be zero, which means the pressure will be the normal atmospheric pressure.
So at which instant it will be atmospheric pressure?
Sorry, come again.
So at which instant it will be atmospheric pressure?
I'll explain. We'll write that down. Just note down up to here. Okay, so let's understand this point in little bit more detail. The pi by 2 phase difference between the displacement wave and the pressure wave. So let's talk about this a little bit more. Means that at a certain instant t equal to t, particles at s equal to plus minus s naught, that is extreme position of oscillation, will experience zero stress. The pressure variation will be zero at that point. And particles at s equal to 0, that is the mean position of the oscillation, will experience p equal to plus or minus p naught, that is extreme compression or rarefaction. So we will understand this point visually also, the diagram kind of situation. Okay, so let's also understand this in this context, that if we look at the graph of the displacement versus time, but remember here the displacement is not along the y-axis. This is only a graph. If you look at a snapshot of the displacement, so here S is actually the longitudinal displacement. Along the x-axis. So suppose that graph at a certain instant of time is looking like this. So we take that to be sine curve. Then before we get into the the pressure wave, let's also visualize how the particles in the medium are located. So what is happening is, if these are, let's say, the mean positions, let's say these represent the mean positions of various medium particles. So imagine these are just imaginary diaphragms of air. Then what is happening is that right now these particles around lambda by 4, they are having maximum displacement along the positive direction. Whereas the ones at 0 and lambda by 2 are having minimum displacement. Then the ones around 3 lambda by 4 are having maximum negative displacement. Then again the ones around lambda are having 0 displacement. Then again the ones around 5 lambda by 4 are having maximum positive displacement. So you can see that this region here is having a compression. Okay. Whereas this region here is having a rarefaction. Likewise, now again this region will have a compression. This region will have a rarefaction. So the compression rarefaction in this case. you see the sequence how it is. Okay, so the corresponding volume stress, or what we call the pressure wave graph, that will be like this. So after some time, the displacement wave would have moved like this. So corresponding the pressure wave also would have moved like this. But they move together in synchronization in such a way that wherever the medium particles are at the mean position part of their oscillation cycle, the pressure is either maximum or minimum. That is, the volume stress is maximum. Either there's a compression maxima or a rarefaction maxima, like that. And wherever the medium particles are at their extreme position of oscillation, that is where the stress is zero. So the pressure is the natural atmospheric pressure. See, wherever you can see from the direction of the arrows, na, Jagannath, wherever the medium particles are pushed together because of displacements. So imagine a section of air which is around this compression. Okay, so both the boundaries from both sides are pushed together at this moment. So there's a compression maximum. Whereas imagine a boundary around this position lambda, a section at this position lambda. The boundaries are pulled. Okay, very good. So at the compression, pressure is maximum. No? There is positive volume stress because the volume is compressed. And at a rarefaction, the volume stress is negative. No? The pressure difference is negative because the volume is expanded. So that's how we know which is a compression, which is a rarefaction. Wherever the air molecules are pressed together, it creates a compression. No? So the volume has decreased from the natural volume. The pressure is increased. That is the concept of Hooke's law. No? Okay, people. So hope this is clear. We'll conclude a few minutes early today at this point. I have something to attend to. So this completes the introduction part of sound. Okay. Though we still have to discuss the intensity of sound waves as part of the introduction. Intensity is something which relates to the loudness of the sound that we hear in terms of the physiological effect of sound. But in terms of physics, intensity is power per unit area of cross section or energy propagating per unit cross sectional area per unit time. So you can think of intensity in a sound wave as something relatable to power that we discussed for a transverse wave, but instead of the power in watts, here we discuss the intensity in watt per meter square. But very much like the average power was proportional to the square of the amplitude, you will see intensity is also proportional to square of amplitude, whether we are talking about the displacement amplitude or the pressure amplitude, because they're proportional to each other. So we'll look at intensity and more things in the next lecture. Okay. Meanwhile, please work out questions from the first chapter of H.C. Verma of waves, that is waves on a string. We'll discuss the doubts of the same also in the next lecture after completing the fundamentals of sound. That's it for today's session, people. Wish you all the best and have a nice day.
Thank you,
Uh,
sir.
thank you.
Bye, sir. Have a nice day, sir.
Have a nice day.
Thank you, sir. Bye.
Thank you, sir. Bye.